Hello everyone. Today we will review from the first exam. First problem. Find the largest and the smallest possible value of probability of A union B and probability of A intersection B. Part A. Probability of A is 0.32 and probability of B is 0.44. We try to find the largest and the smallest value for probability of A union B and A intersection B. Let's find the values for probability of A union B first. We know that probability of A union B, it must be greater than both probability of A and probability of B. And here probability of A is 0.32 and probability of B is 0.44. So probability of A union B must be greater than both numbers. Since probability of A union B must be greater than both numbers, it must be greater than the larger one. When it's greater than 0.44, it's guaranteed it's greater than 0.32. Now on the other side, probability of A union B must be less or equal to probability of A plus probability of B. Probability of A plus probability of B, if we add them up here, we get 0.76. And also, probability of A union B must always be less than 1. So since probability of A union B is less than both numbers, it must be less than the smaller one. So probability of A union B must be less than 0.76. When it's less than 0.76, it's guaranteed it's less than 1. Next, we try to find the largest and the smallest possible value for probability of A intersection B based on what we have here. We know that the relationship between probability of A union B and probability of A intersection B is probability of A union B equal to probability of A plus probability of B minus probability of A intersection B. In this equation, if I try to isolate probability of A intersection B, this equation can be rewritten as probability of A intersection B equal to probability of A plus probability of B minus probability of A union B. So here in this equation we can see that when probability of A union B has a minimum, A intersection B here will have a maximum. When A union B has a maximum, A intersection B will have a minimum. So when probability of A union B equal to 0.44, probability of A intersection B will have a maximum. So probability of, use the formula, probability of A intersection B equal to probability of A plus probability of B minus probability of A union B. If I plug in the numbers, probability of A is 0.32, probability of B is 0.44, probability of A union B here is 0.44. Subtract, I get 0.32. And when the probability of A union B has a minimum, probability of A intersection B will have a maximum. So this is the largest possible value. Now, when probability of A union B is 0.76, I can use the same equation, find probability of A intersection B. Then plug in the values. Probability of A is 0.32. Probability of B is 0.44. Minus probability of A union B. Probability of A union B here is 0.76. And when we subtract, we get 0. So when probability of A union B has a maximum, probability of A intersection B will have a minimum. So that's the smallest possible value. That's the smallest possible value of probability of A intersection B. Hence, we can say probability of A intersection B is between 0 and 0.32. That's the minimum, that's the maximum. Part B. Probability of A is 0.7. Probability of B is 0.65. Find the largest and the smallest possible value for probability of A union B and probability of A intersection B. Let's find the values for probability of A union B first. We know that probability of A union B must be greater than both probability of A and probability of B. Probability of A is 0.7. Probability of B is 0.65. So we know that probability of A union B must be greater than both numbers. Since probability of A union B must be greater than both numbers, it must be greater than larger number. If probability of A union B is larger than 0.7, it's guaranteed it's greater than 0.65. So it must be greater than the larger number. On the other hand, probability of A union B must be less than probability of A plus probability of B. If we add them up, probability of A plus probability of B is 1.35. Also, we know that probability of A union B must always be less than 1, less or equal to 1. Then, since probability of A union B is less than both numbers, it must be less than the smaller number. When it's less than 1, it's guaranteed it's less than 1.35. So it must be less than the smaller number. So that's the smallest and the largest possible value for probability of A union B. Next, let's try to find the largest and the smallest possible value for probability of A intersection B based on what we have here. We know that the relationship between probability of A union B and A intersection B is probability of A union B equal to probability of A plus probability of B minus probability of A intersection B. If we solve this equation for probability of A intersection B, this equation can be rewritten as probability of A intersection B equal to probability of A plus probability of B minus probability of A union B. And when probability of A union B has a minimum, probability of A intersection B will have a maximum. When probability of A union B has a minimum, probability of A intersection B will have a maximum. So when probability of A union B equal to 0.7, probability of A intersection B equal to probability of A plus probability of B minus probability of A union B. If we plug in the numbers, we have 0.7 plus 0.65 minus 0.7. Probability of A union B is 0.7 here. Then if we add and subtract, we get 0.65. So when probability of A union B has a minimum, probability of A intersection B will have a maximum. That's the largest possible value. When probability of A union B has a minimum, probability of A intersection B will have a maximum. So that's the largest possible value for probability of A intersection B. Next, when probability of A union B equal to 1, probability of A intersection B equal to probability of A plus probability of B minus probability of A union B. If we plug in the values, we get 0.7 plus 0.65 minus probability of A union B, which is 1. So 0.7 plus 0.65 is 1.35. 1.35 minus 1 is 0.35. So when probability of A union B has a maximum, probability of A intersection B will have a minimum. So that's the smallest possible value for probability of A intersection B. That's the smallest possible value for probability of A intersection B. Since that's the largest possible value, that's the smallest possible value. So we know that probability of A intersection B is between 0.35 and 0.65. That's the smallest possible value, and that's the largest possible value. Number 2, part A. Assume probability of A is 0.64, probability of B is 0.48, and probability of intersection B is 0.33. Find probability of A union B, A intersection B complement, and A union B complement. Let's find probability of A union B first. We know that probability of A union B is always probability of A plus probability of B minus probability of A intersection B. If we plug in the values, we have 0.64 plus 0.48 minus 0.32, 0.33. Then use calculator. I get 0.79 here. Next, probability of A intersection B complement. If we use a Venn diagram, we can see that probability of A intersection B complement looks like this. Let's set A, let's set B. A intersection B complement is this part. It's everything in A, but not in B. So the shaded region can be written as probability of A minus probability of A intersection B. The shaded region can be written as probability of A take away probability of A intersection B. Probability of A is 0.64. Probability of A intersection B is 0.33. So when we subtract, we get 0.31. That's probability of A intersection B complement. Next one, probability of A union B complement. Probability of A union B complement. Apply this formula here. Treat this as A, treat this as B. So we have probability of A plus probability of B complement minus probability of A intersection B complement. Apply the same formula here. We treat the second set as B. Probability of the first set plus probability of the second set minus probability of their intersection. Then plug in. We know that probability of B complement is 1 minus probability of B. Probability of B complement is 1 minus probability of B minus probability of A intersection B complement. Then plug in numbers. Probability of A is 0.64. Probability of B is 0.48 minus probability of A intersection B complement, which we just found here. That's 0.31. Then I use my calculator. I get 0.85 here. That's the probability of A union B complement. Number 2, part B. Assume probability of A union B is 0.87 and probability of A union B complement is 0.63. Find probability of A. So here, what's given is probability of A union B. Probability of A union B can be rewritten as probability of A plus probability of B minus probability of A intersection B, which equal to 0.87. Probability of A union B complement can also be rewritten using the same formula. Probability of A union B complement can be rewritten as probability of A plus probability of B complement minus probability of A intersection B complement, and that equal to 0.63. Now, if I add these two equations together, I have twice probability of A plus probability of B plus probability of B complement. For these two terms, we have minus probability of A intersection B plus probability of A intersection B complement then on the right side, 0.87 plus 0.63, I get 1.5. Next, I have 2 times probability of A plus probability of B plus probability of B complement is always 1. Here, what's probability of A intersection B plus probability of A intersection B complement? Let's look at a Venn diagram. Assume that's set A, let's set B. A intersection B is a set here. That's intersection B. A intersection B complement, that's everything in set A, but not in set B. That's this part. If I add them up, I get probability of set A. If I add these two sets together, I get probability of set A. And that equal to 1.5. Here we can see that twice probability of A minus probability of A is probability of A. So we have probability of A plus 1 equal to 1.5. If I solve this equation for probability of A, I get 0.5. So probability of A is 0.5. Number 3, part A. Show that probability of A minus B plus probability of B minus A equal to probability of A union B minus probability of A intersection B. So here, we try to show left side equal to the right side. So left side, probability of A minus B plus probability of B minus A. Let's rewrite this step first. Probability of A minus B represent everything in set A, but not in set B. Let's set A, let's set B. Probability of A minus B is everything in set A, but not in set B. This region can be written as probability of A take away A intersection B. Probability of A minus B can be written as probability of set A take away the intersection of A intersection B. Take away probability of A intersection B. Similarly, for probability of B minus A, that's everything in set A, everything in set B, but not in set A. Probability of B minus A, that's everything in set B, but not in set A. That's this region here. For this region, I can use probability of B minus probability of A intersection B. Here I can use probability of set B minus probability of A intersection B. That's probability for the set B minus A. Next, by associative law, this can be rewritten as probability of A plus probability of B minus probability of A intersection B twice. And the first three set together, probability of A plus probability of B minus probability of A intersection B. This is probability of A union B. And last set stays the same. So here we prove that left side equal to the right side. Number 3, part B. Show that probability of A union B union C equal to probability of A plus probability of B plus probability of C minus probability of A intersection B minus probability of A intersection C minus probability of B intersection C plus probability of A intersection B intersection C. We try to use this formula to prove this. So probability of A union B union C, it can be rewritten as probability of A union B union C. A union B union C can be written as A union B union C. That's associative law. Then use this formula. We treat this as set A, this as set B. So that equal to probability of the first set plus probability of the second set minus probability of the intersection of both sets. We treat this as first set, this is second set. Probability of A union B, the formula is always probability of the first set plus probability of the second set minus probability of the intersection of both sets. So probability of the first set plus probability of the second set minus probability of the intersection of two sets. Now, the first part, probability of A union B, that's probability of A plus probability of B minus probability of A intersection B. Probability of set C stays the same. For this part here, probability of A union B intersection C, it can be rewritten as probability of A intersection C union B intersection C. By distribute property, I distribute set C into the parentheses. We have A intersection C union B intersection C. Let's distribute property. I distribute C into the parentheses. We have A intersection C union B intersection C. That's what we have here. Now next, we keep the first part the same. Probability of A plus probability of B minus probability of A intersection B plus probability of C minus this guy. Let me put it here. Probability of A intersection C union B intersection C. This is union of two sets. We can use this formula again. I treat this as set A, treat this as set B. So this can be rewritten as probability of the first set plus probability of the second set minus probability of the intersection of both sets. So use this formula again. We have probability of one set union another set. Use this formula is probability of the first set plus probability of the second set minus probability of the intersection of both sets. Then the first two parts I leave it the same. A intersection B plus B intersection C. I leave it the same. For the last step here, apply associative law. Since all operations here looks exactly the same, apply associative law. It can be rewritten as probability of A intersection B intersection probability of intersection C intersection C. So this can be rewritten as probability of A intersection B intersection C intersection C. Since all operations are the same, by associative law, I can put this in different orders. So we have probability of A intersection B intersection C intersection C. And we know that the set C intersection C is C. Set C intersection set C is C. So together we have probability of A intersection B plus probability of B intersection C minus probability of A intersection B intersection C. A intersection B intersection C. So the last part here equal to this. The last part equal to this. So if I bring this down, we have probability of A plus probability of B minus probability of A intersection B. Then we switch these two sets, put C in the front, plus probability of C minus probability of A intersection B. What's in the parentheses here is this expression. This expression is these three sets here. Probability of A intersection B. Sorry, this is A intersection C. Probability of A intersection C plus probability of B intersection C minus probability of A intersection B intersection C. Then finally, if I distribute negative sign, it can be rewritten as probability of A plus probability of B plus probability of C minus probability of A intersection B minus probability of A intersection C minus probability of B intersection C plus probability of A intersection B intersection C. Number 4. Tom is currently taking an English reading class and an English writing class. He estimates that the chance that he will pass each class is 60% and 80% respectively. And he also estimates that the chance he will fail both classes is 50%. Assume his estimation is correct. Find the following probabilities. So let's set out the problem first. Let event A represent that Tom will pass his English reading class. Let event B represent that Tom will pass his English writing class. What's given is that probability of A, the chance that Tom will pass his reading class is 60%, which is 0.6, that's given. Probability of B, the chance Tom will pass his writing class is 80%, which is 0.8, that's given. And he also estimated that the chance he will fail both classes is 50%. That means the probability that he will not pass reading class and he will not pass his writing class is 15%. The chance that he will not pass his reading class and he will not pass his writing class is 15%. That's what's given. Now, part A. What we are looking for is what's the probability that Tom will pass both classes. What we are looking for is the chance that Tom will pass his reading class and pass his writing class. So that's what we are looking for here. That's what's given. That's what we are looking for. So based on given information, let's simplify this expression first. We know that probability of A complement intersection B complement is 15%. It's 0.15. If I use De Morgan's law, this expression can be rewritten as probability of A union B complement is 15%. That means 1 minus probability of A union B is 15%. Solve this equation for probability of A union B. Probability of A union B is 0.85. That's what we get from this information here. Next, we are looking for probability of A intersection B. We know that there's a formula that says probability of A union B is always probability of A plus probability of B minus probability of A intersection B. That's a formula. If we solve this equation for probability of A intersection B, this equation can be rewritten as probability of A intersection B equal to probability of A plus probability of B minus probability of A union B. We know probability of A, we know probability of B, and we know probability of A union B. We can plug in find probability of A intersection B. So probability of A is 0.6. Probability of B is 0.8. Probability of A union B is 0.85. Then subtract. We get 0.55. That's the chance that Tom will pass both classes. That's the chance that Tom will pass both classes. Part B. What's the probability that Tom will pass only one of the classes? Part B. What's the probability that Tom will pass only one of the classes? the chance he only passed one of the classes. That means either he passed his writing class, either he passed his reading class, but not pass his writing class, or he passed his writing class, but he doesn't pass his reading class. Either he passed reading class, failed the writing class, or passed the writing class and failed the reading class. Let's rewrite these sets here. We can use a Venn diagram. Let's set A, let's set B. A intersection B complement is this part. Everything in A, but not in B. A intersection B complement is everything in A, but not in B. This can be rewritten as probability of A take away A intersection B. This can be rewritten as probability of A take away A intersection B. And probability of B intersection A complement is this part. Everything in B, but not in A. This can be rewritten as probability of B take away probability of A intersection B. Then plug in the numbers. Probability of A is 0.6. A intersection B from part A we know is 0.55. Probability of B is 0.8 minus probability of A intersection B from part A we know that's 0.55. So we get 0.05 plus 0.25. Together is 0.3. That's part B. Part C. If it's known that Tom passed his reading class, what's the probability that he also passed his writing class? So this is conditional probability. Something is given. If it's known that Tom passed his reading class, so what's given is that Tom passed his reading class. What's the probability that he also passed his writing class? So that's all we are looking for. Given he passed his reading class, what's the probability that he passed his writing class? Then use the formula. This can be rewritten as probability of A intersection B over probability of A. What's given is always the denominator. What's given here is always the denominator. Then plug in. Probability of A intersection B is 0.55. Probability of A is 0.6. Then use calculator. That's 11 over 12. Part D. If it's known that Tom failed his reading class, what's the probability that he also failed his writing class? Again, this is a conditional probability. Some condition is given here. If it's known that Tom failed his reading class, so it's given that Tom doesn't pass his reading class. What's the probability that he also failed his writing class? We are looking for the probability that he also failed his writing class. Then use the formula for conditional probability. That's probability of A complement intersection B complement over probability of A complement. Probability of A complement intersection B complement is given to be 0.15. That's given. The chance that he failed both classes is 0.15. It's 15%. Then plug in. That's 0.15 on the numerator. Probability of A complement. That's 1 minus probability of A. That's 1 minus probability of A. 1 minus 0.6. That's the denominator. Then we have 0.15 over 0.4. Use calculator. We have 3 over A. Number 5. Given a set of digits 0, 1, 3, 5, 6, 8, 9. Given a set of digits 0, 1, 3, 5, 6, 8, 9. And a 4-digit number is formed using the digits in the set without repetition. Without repetition means use every digit exactly once. Note, a 4-digit number cannot start with a 0. For example, a 4-digit number must be 1379. That's 1379. That's called a 4-digit number. If a number starts with a 0, 0769. This is a 3-digit number. This number is the same, 769. This is a 3-digit number. This is not 4-digit number. So a 4-digit number cannot start with a 0. A 4-digit number cannot start with a 0. We randomly choose 4 digits from the set and form a 4-digit number. And we are looking for the following probabilities. Number 5, part A. What's the probability that the number is even? Keep in mind, probability is always the set of favorable outcome divided by the set of all possible outcome. Let's find the set of all possible outcome first. The number of all possible outcome. The number of all possible outcomes. We try to form a 4-digit number using these digits. A 4-digit number cannot start with a 0. So the first digit cannot be 0. It could be 1, 3, 5, 6, 8, 9. So there are 6 choices for the first digit. It cannot be 0. There are 6 choices for the first digit. This 6 means there are 6 choices for the first digit. Next, for the next digit, since I use one of the digit here, and the next digit could be 0. Since I use one of the digits, so there are 6 choices for the next digit. And then since I use 2 of the digits, there are 5 digits left. For the next digit, there are 5 choices. And similarly, for the last digit, there are 4 choices. Together is 720. So the number of all possible outcomes is 720. Now, number of favorable outcomes is the number of even numbers. How many even numbers can we obtain? How many even numbers can we obtain? If a number is even, the last digit must be even. If a 4-digit number is even, the last digit must be even. So the last digit could be 0, 6, or 8. If a number is even, its last digit must be even. So its last digit must be 0, 6, or 8. If I choose 0 here, if I pick 0 for the last digit, then in the first digit, it could be 1, 3, 5, 6, 8, 9. There are 6 choices. If I pick 0 in the last place, then there are 6 choices. The first digit could be 1, 3, 5, 6, 8, 9. There are 6 choices. Now, but however, what if I pick 6 in the last place? If I put number 6 in the last place, then how many choices do I have in the first place? If I put number 6 here, then in the first place I cannot use 6 again. And we know that for a 4-digit number, first place cannot be 0. So I can choose 1, 3, 5, 8, and 9 in the first place. If I pick 6 in the last place, I have 5 choices in the first place. But if I pick 0 in the last place, I have 6 choices in the first place. So here, the choice in the last place affect the choice in the first place. We must consider 2 cases. Here, since the choice in the last place affect the choice in the first place, we must consider 2 cases. Case 1. The last digit is 0. Case 2. Last digit is not 0. If it's not 0, it must be even, then it must be either 6 or 8. So there are 2 cases. The last digit could be either 0 or non-zero. If it's non-zero, since it must be even, it must be either 6 or 8. Now let's think of this problem over. If I put 0 in the last place, there's only one choice. If I put 0 in the last place, there's only one choice. I can only choose 0, there's only one choice. And if I choose 0 in the last place, for the first place, it could be 1, 3, 5, 6, 8, 9. So there are 6 choices in the first place. For the second place, since I use 2 of the digits, for the next place I have 5 choices. Since I use 2 of the digit already, next place I have 5 choices. Then for the last digit, since I use 3 digits already, there are totally 7 digits. Since I use 3 digits already, there are 4 digits left. So there are 4 choices here. Second case, if the last digit is either 6 or 8, there are 2 choices. There are 2 choices. It could be either 6 or 8. There are 2 choices. Then, if I choose 6 or 8, in the first place, since it cannot be 0, there are 5 choices. If I choose 6 or 8 in the last place, in the first place it cannot be 0. So there are 5 choices in the first place. Then, since there are totally 7 digits, I choose 2 digits already. There are 5 choices here. Then, from the last digit, since I use 3 digits already, there are 4 choices here. Since there are 2 cases, we can add them up. So by counting principle, we multiply, then add them up. 6 times 5 times 4, that's 120. 5 times 5 times 4 times 2, that's 200. Together is 320. So that's the number of favorable outcome. That's the number of all possible outcome. The answer is 320 over 720, which is 4 over 9. Probability is always number of favorable outcome divided by number of all possible outcome. Part B. What's the probability that the number is odd and greater than 5,000? Probability is always number of favorable outcome divided by number of all possible outcome. The number of all possible outcome is the same as the previous part. A 4-digit number cannot start with a 0. So first digit has 6 choices. Second digit, since we use 1 digit already, and it could be 0. So there are 6 choices. Next digit, 5 choice, 4 choice, which is 720. Multiply together by counting principle, which is 720. That's the number of all possible outcomes. Then for the number of favorable outcome, we are looking for number of odd numbers, which is greater than 5,000. For number of favorable outcome, we are looking for number of odd numbers, which is greater than 5,000. Number of odd numbers, which are greater than 5,000. So let's think of the problem this way: 1, 2, 3, 4. If a number is an odd number, the last digit must be odd. Since it's odd, it could be 1, 3, 5, 9. Since it's odd, it could be 1, 3, 5, 9. So the last digit could be 1, 3, 5, 9. If a number is greater than 5,000, the first digit must be greater than 5. If a number is greater than 5,000, the first digit must be 5 or more. So the first digit could be 5, 6, 8, 9. If a number is greater than 5,000, the first digit must be 5, 6, 8, 9. Let's try some simple choice first. In the first digit, if I choose 1, in the last digit, if I choose 1 as the last digit, then in the first place, I can use 5, 6, 8, 9. There are 4 choices in the first. There are 4 choices for the first digit. Now, in the last place, what if I pick 9? In the last place, what if I pick 9? If I pick 9 from the last place, then I cannot use 9 in the first place. In the first place, it could be 5, 6, 8, 9. Since I cannot use 9, there's only 3 choices. If I put 9 in the last place, I cannot use 9 in the first place. So in the first place, it must be 5, 6, or 9. 5, 6, or 8, there's only 3 choices. But if I put 1 in the last place, the first place could be 5, 6, 8, 9. There are 4 choices. Since the choice in the last place affects the choice in the first place, we must consider 2 cases. Here we can see that 5 and 9 is common in both sets. 5 and 9 is common in both places. So considering 2 cases. Since 5 and 9 is common in both places, let's consider the last place could be either 5, 9 or 1, 3. Since last place must be odd, let's consider 2 cases. Last place could be either 5, 9 or 1, 3, because 5, 9 is also a choice in the first place. So we split the last digit in 2 cases, 5, 9 or 1, 3. Now, if I choose 5 or 9 in the last place, there's only 2 choices. It could be either 5 or 9. In the first place, since the number must be greater than 5,000, it must be 5, 6, 8, or 9. It must be 5, 6, 8, or 9. Since I choose one of 5 or 9 in the last place, in the first place there's only 3 choices. Since I choose 5 or 9 in the last place, in the first place there's only 3 choices. Because I use one of these numbers, 5 or 9, there's only 3 choices in the first place. Then there are totally 7 digits. If I use 2 of the digits here, we have 5 choices for the next digit. Then since there are 7 digits, we use 3 digits already. For the last place, we have 4 choices. Case 2. If I choose 1 or 3 in the last place, there are 2 choices. If I choose 1 or 3 in the last place, since the number must be greater than 5,000, in the first place it could be 5, 6, 8, 9. Since I choose 1 or 3 in the last place, in the first place it could be 5, 6, 8, 9. There are 4 choices in the first place. There are 4 choices in the first place. Then there are totally 7 digits. Since I use 2 of the digits, we have 5 choices from the next place. And similarly, we have 4 choices from the last place. Then by counting principle, multiply them out, and then add them up. 3 times 5 times 4 times 2, that's 120. 4 times 5 times 6 times 2, that's 160. 120 plus 160 is 280. So probability is always number of feasible outcome divided by number of all possible outcome. The answer is 280 over 720, which is 7 over 18. Using my calculator, I get 7 over 18. Number 5, part C. What's the probability that the number is less than 5,600? We know that probability is always number of feasible outcome divided by number of all possible outcome. Let's find the denominator first, the number of all possible outcomes. Here we have 7 digits, 0, 1, 3, 5, 6, 8, 9. We try to use these digits to form a 4-digit number without repetition. For a 4-digit number, first digit cannot be 0, so there are 6 choices. Second digit, it could be 0, but we use one of the digit already, so there are 6 choices for the second digit. For the third digit, there are 5 choices because we use 2 of the digit already, and for the last digit, there are 4 choices. Then, by counting principle, multiply this number together. 6 times 6 times 5 times 4 is 720. That's the denominator, the number of all possible outcomes. Now for the numerator, the number of feasible outcomes, we're looking for the number of numbers which is less than 5,600. We're looking for the number of numbers which is less than 5,600. we know that if a 4-digit number is less than 5,600, its first digit must be 5 or less. If a 4-digit number is less than 5,600, its first digit must be 5 or less. If the first digit is 5, then the second digit could be any second digit must be less than 6. If the first digit is 5, the second digit must be less than 6. But if the first digit is not 5, it's less than 5. If the first digit is less than 5, if the first digit is less than 5, then for the second digit it could be anything. No matter what we put here, this number is always less than 5,000. Hence, it's less than 5,600. So consider two cases. If the first digit is 5, there's only one choice. There's only one choice for 5. Then the second digit must be less than 6. If the first digit is 5, second digit must be less than 6. Since we use 5 already for the first digit, second digit must be less than 5, must be less than 6. Less than 6, it could be either 0, 1, or 3. If it's less than 6, it could be 0, 1, or 3. We use number 4 already, we can use it again. So the second digit could be either 0, 1, or 3. There are 3 choices. For the rest, it could be anything. There are totally 7 digits. We use 2 of the digits. Then for the next digit, there are 5 choices. For the next digit, there are 4 choices. Now, case 2. If the first digit is less than 5, since it cannot be 0, the first digit cannot be 0, and it's less than 5, it must be either 1 or 3. And the first digit must be either 1 or 3. So there are 2 choices in the first place. Since the first digit is less than 5, and it cannot be 0, it must be either 1 or 3. So there are 2 choices for the first digit. Since the first digit is less than 5, the second digit could be any number. And we know that there are totally 7 digits. If we use one of the digits for the second place, there are 6 choices. Then for the next place, since I used 2 of the digits already, there are 5 choices here, 4 choices here. Then by counting principle, we multiply this number up together and then add them up. 1 times 3 times 5 times 4, that's 60. 2 times 6 times 5 times 4, that's 240. Together it's 300. So that's the number of favorable outcome. Probability is always number of favorable outcome divided by number of all possible outcome. So we get 300 over 720, which is 5 over 12. Part D. If it's known that the number is even, what's the probability that it's greater than 5,000? This is conditional probability. One condition is given here. If it's known that the number is even, what's the probability that it's greater than 5,000? So this is conditional probability. Let A be the event that the number is even. Let A be the event that the number is even. Let B be the event that the number is greater than 5,000. Let A be the event that the number is even. Let B be the event that the number is greater than 5,000. Then this is conditional probability. It can be written as probability of, if it's known that the number is even, given the number is even, what's the probability that the number is greater than 5,000? So that's what we are looking for. We have probability of B given A. Given the number is even, what's the probability that the number is greater than 5,000? Then use the formula for conditional probability. That's probability of A intersection B over probability of A. The denominator is always the condition here. Given that the number is even, that's always the denominator. Then we find each probabilities. We find each probabilities individually and then divide. Usually, let's find the denominator first. What's probability of A? Probability of A is the probability that the number is even. Probability of A is the probability that the number is even, which is the same as part A here. What's the probability that the number is even? So the answer from part A is 4 over 9, or 320 over 720. That's the solution from part A. That's the probability that the number is even. That's from part A. That's the probability that the number is even. Now let's find the numerator. What's the probability that the number is even and it's greater than 5,000? What's the probability that the number is even and greater than 5,000? So for probability of A intersection B, for this probability is always number of favorable outcome divided by number of all possible outcome. The number of all possible outcome here is the same as the previous parts. We have 4 digits. First digit cannot for 4-digit number. First digit cannot be 0. So there are 6 choices. It could be 1, 3, 5, 6, 8, 9. There are 6 choices. Second digit it could be 0, but we use one of the digit already. So there are 6 choices. Next digit 5 choices, 4 choices. By counting principle, multiply together. That's 720. That's the number of all possible outcomes. Now for the number of favorable outcome, we are looking for the number of even number, which is greater than 5,000. The number of even numbers greater than 5,000. We're looking for the number of even numbers greater than 5,000. If a number is greater than 5,000, the first digit must be 5 or more. If a number is greater than 5,000, the first digit must be 5 or more. So it must be 5, 6, 8, 9. And if a number is even, the last digit must be even. If a number is even, the last digit must be even. It must be 0, 6, or 8. If a number is even, if a 4-digit number is even, its last digit must be even. So it must be 0, 6, or 8. Then here, if I pick 0 in the last place, then in the first place it could be either 5, 6, 8, or 9. There are 4 choices. If I pick 0 in the last place, in the first place there are 4 choices. But what if I pick 6 in the last place? If I pick 6 in the last place, in the first place I cannot use 6 again. So if I use 6 in the last place, in the first place it must be 5, 8, or 9. There's only 3 choices. So here we can see that if I pick 0 in the last place, in the first place I have 4 choices. But if I pick 6 in the last place, then in the first place there's only 3 choices. Since the choice in the last digit affect the choice in the first digit, we must consider 2 cases. Since the choice in the last place affect the choice in the first place, we must consider 2 cases. Case 1, if the last digit is 0. Case 2, if the last digit is not 0. If the last digit is not 0, then it must be 6 or 8. Case 1. If the last digit is 0, there's only one choice. There's only one 0. There's only one choice for the last place. Then in the first place, since it must be greater than 5,000, it could be 5, 6, 8, 9. So there are 4 choices. If I choose 0 in the last place, there's 4 choices in the first place. Then for the rest, it could be any numbers. Since there are 7 digits together, I use 2 of them. There are 5 digits left. So for the next place, there are 5 choices. Then for the next place, there are 4 choices. Now, second case. If the last digit is either 6 or 8, then we have 2 choices. If the last digit is either 6 or 8, I have 2 choices. Since I use one of these numbers, 6 or 8, and the first digit must be greater than 5. There are 4 choices, but I use one of these numbers, so there's only 3 choices left. So for the first place, there are only 3 choices left. Then for the rest, it could be any numbers. Since there are totally 7 digits, I use 2 of the digits. There are 5 digits left. So for the next place, there are 5 choices. Next place, there are 4 choices. Then by counting principle, we multiply this together and then add them up. 4 times 5 is 4 times 5 times 4. That's 80. 3 times 5 times 4 times 2. That's 120. I got 200. So probability of A intersection B. Probability of A intersection B. Number of favorable outcomes divided by number of all possible outcomes. 200 over 720. And the final answer. Probability of B given A. The final answer. Probability of B given A. That's probability of A intersection B. Probability of A intersection B over probability of A. Probability of A intersection B is 200 over 720. Probability of A is 320 over 720. Then since they have the same denominator, I can cancel denominator. I get 200 over 320. Then use calculator. 200 over 320 is 5 over A. If the number is even, the chance the number is greater than 5,000 is 5 over A. Number 6. A hand of 5 cards is dealt to each of 3 players from a standard deck of 52 cards. Part A. What's the probability that at least one player receives at least 1 heart? Part A. What's the probability that at least one player receives at least 1 heart? If we try to solve this problem directly, at least one player receives at least 1 heart. It could be one player receives 1 heart, one player receives 3 hearts, or 2 players each receive 2 hearts, or 3 players each receive 3 hearts. It may be too many cases, too complicated. Think of the complement. Let event E be the event that at least let E be the event that at least one of the players receives at least 1 heart. At least one of the players receive at least 1 heart. Now think of the complement. What's E complement? E complement represent no player receive any hearts. Its complement. E complement represent no player receive any hearts. Its complement represent no player receive any hearts. Let's try to find the probability of the complement of E complement. Probability that no player receive any hearts. Keep in mind, probability is always number of favorable outcome divided by the number of all possible outcome. Let's find the number of all possible outcome first. There are totally 52 cards. Each player draw 5 cards. So first player first of all choose 5 cards out of 52 cards. That's the number of ways that the first player choose 5 cards out of 52. That's the number of ways that the first player receive 5 cards out of 52. 52 choose 5. Since from the cards in your hand, order doesn't matter. It's combination. So 52 choose 5. That's the number of ways that the first player receive 5 cards out of 52. Then next, after the first player get 5 cards, in the deck there are 47 cards left. Second player choose 5 hearts from what's left. Then after the second player make choice, there are 42 cards left on the deck. Then the third player make choice. The third player choose 5 cards out of 42. That's the denominator, the number of all possible outcome. Then the numerator, number of favorable outcome. No player receive any hearts. Since they cannot choose hearts, they can choose club, spade, or diamond. So there are 39 available cards for them. There are 39 available cards. They cannot choose heart, but they can choose spade, club, or diamond. Each suit has 13 cards. 13 times 3 is 39. So there are 39 available cards. First player choose 5 cards out of these 39 available cards. That's the number of ways he chose 5 available cards out of 39. Second player chose from the remaining cards. There are totally 39 cards. If the first player chose 5 cards, there are 34 cards left. So the second player chose 5 cards out of 34. After the second player makes choice, there are 29 cards left. Then the third player chose 5 cards out of what's left here. So that's the number of ways. The first player makes choice, second player makes choice, third player makes choice. Then by counting principle, multiply them together. Here I use my calculator. I get 0.0056. Then for probability of E, I use 1 minus probability of E complement. That's 1 minus 0.0056, which is 0.9944. That's the probability that at least one player receives at least 1 heart. Part B. What's the probability that at least one player receives 5 hearts? So let event A represent that the first player receive 5 hearts. Let event B represent the second player receive 5 hearts. Let event C represent that the third player receive 5 hearts. What we are looking for is the probability that at least one player receive 5 hearts. That's the probability that either the first player receive 5 hearts, or the second player receive 5 hearts, or the third player receive 5 hearts. either the first player or the second player or the third player receive 5 hearts. Then use the formula for inclusion and exclusion. This formula can be rewritten as probability of A plus probability of B plus probability of C minus probability of A intersection B minus probability of A intersection C minus probability of B intersection C plus probability of A intersection B intersection C. Let's find each probability individually, then add them up. What's probability of A? Probability of A is the probability that the first player receives 5 hearts. So probability is always number of favorable outcome divided by number of all possible outcome. Number of favorable outcome divided by the number of all possible outcome. For the number of all possible outcomes, there are 3 players. Each player gets 5 cards from a standard 52 card deck. So for the first player chose 5 cards out of 52. First player receives 5 cards out of 52. Then there are 47 cards left. The second player receives 5 cards from the remaining cards. Then there are 42 cards left. The third player receives 5 cards out of 42. The third player receives 5 cards out of 42. That's the number of all possible outcomes. For the number of favorable outcome, we want first player receives 5 cards. First player receives 5 hearts. There are totally 13 hearts. First player chooses 5 of the hearts. There are totally 13 hearts. First player chooses 5 of the hearts. Now for the second player, we don't care. They may or may not receive hearts. After first player chooses 5 hearts, we put the rest of the hearts back. So on the deck, right now there are 47 cards left. Second player chooses 5 cards. He may or may not receive hearts. Then there are 42 cards left. The third player chooses 5 cards out of 42. He may or may not receive any hearts. We don't care. Then simplify. We get 13 choose 5 over 52 choose 5. That's the probability that the first player receives 5 hearts. That's the probability that the first player receives 5 hearts. Similarly, the probability that the second player receives 5 hearts or the third player receives 5 hearts must be the same. So probability of A, B, C, they're all the same. Probability that first player receives 5 hearts, second player receives 5 hearts, or the third player receives 5 hearts, they're exactly the same. Next, let's try to find out probability of A intersection B. Probability of A intersection B represent probability that the first player receives 5 hearts, the second player receives 5 hearts. We don't care about the third player. First player receives 5 hearts, second player receives 5 hearts. Probability is always number of favorable outcomes divided by number of all possible outcomes. For the number of all possible outcomes, we have 3 players. Each player receives 5 hearts, which is the same as what we have here. 52 choose 5, 47 choose 5, and 42 choose 5. That's the denominator, the number of all possible outcomes. Then for the numerator, number of favorable outcomes, we want first player receive 5 hearts, and the second player receive 5 hearts. We don't care about the third player. Then we know that there are totally 13 hearts. First player choose 5 hearts out of 13. Second player, for the second player, since first player already chose 5 hearts, there are 8 hearts left. For the second player, since the first player already picked 5 hearts, 13 minus 5 is 8, so there are 8 hearts left for the second player. Second player also picked 5 hearts. That's the probability that first player receives 5 hearts, second player receives 5 hearts. But we don't care about the third player. The third player, he may or may not receive hearts. The third player, he may or may not receive hearts. Since first player chooses 5 hearts, second player chooses 5 hearts. There are a few hearts left. We put the hearts back to the deck. There are totally 52 cards. Since they already picked 10 cards, there are 42 cards left. There are totally 52 cards. Each first and the second player, they both pick 5 hearts. There are 42 cards left for the third player. The third player, he may or may not receive hearts. We don't care. So he chooses 5 cards out of 42 cards. Then cancel 42, choose 5. What's left is 13 choose 5 times A choose 5 over 52 choose 5 times 47 choose 5. That's the probability that the first player and the second player, they both receive 5 hearts. And similarly, probability of A intersection C, B intersection C is the same. So we know that probability of A intersection B is the same as probability of A intersection C. It's the same as probability of B intersection C. They are all equal to 13 choose 5, A choose 5, 52 choose 5, 47 choose 5. Next, let's try to find probability of A intersection B intersection C. Probability of A intersection B intersection C. Let me present the probability that all 3 players, each player receive 5 hearts. All 3 players, each player receive 5 hearts. Is it possible? There's only 13 hearts. It's impossible to give every 3 players, each player 5 hearts. Then we need 15 hearts. So that's impossible. Since there's only 13 hearts, it's not enough to give every 3 players 5 hearts. So this is impossible. Then use the formula. Probability of A union B union C equal to probability of A plus probability of B plus probability of C. Since they're all the same, we have 3 times 13 choose 5 over 52 choose 5 minus probability of A intersection B, probability of A intersection C, and probability of B intersection C. Again, since they're all the same, we can do minus, here we can do minus 3 times 13 choose 5, A choose 5, 52 over 52 choose 5, times 47 choose 5, plus probability of A intersection B intersection C, that's 0. Then here I use my calculator. I get 0.001486. I get 0.001486. Part C. What's the probability that at least one player receives exactly 2 hearts? So very similar. The event A represents that the first player receives exactly 2 hearts. The event B represents the second player receives exactly 2 hearts. The event C represents the third player receives exactly 2 hearts. What we are looking for is probability that at least one player receives exactly 2 hearts. So what we are looking for is probability of A union B union C. Either the first player or the second player or the third player receive exactly 2 hearts. At least one player. Either the first player or the second player or the third player receive exactly 2 hearts. Then use the formula for inclusion and exclusion. That's probability of A plus probability of B plus probability of C minus probability of A intersection B minus probability of A intersection C minus probability of B intersection C, then plus probability of A intersection B intersection C. We try to find each probability individually, then add them up. We try to find each probability individually, then add them up. How do we find probability of A? Remember, probability is always number of favorable outcome divided by number of all possible outcomes. For the number of all possible outcomes, we know there are 3 players. Each player receives 5 cards from a standard deck of 52 cards. So the number of all possible outcomes is 52, choose 5. That's the number of ways that first player receives 5 cards from the deck, from the standard deck. Then there are 47 cards left. The second player will choose 5 cards out of 47. That's the number of ways. Then the second player makes choice. Then there are 42 cards left on deck. The third player will choose 5 cards out of 42. That's the number of ways. Then the third player makes choice. So that's the denominator, the number of all possible outcomes. Now for the numerator, number of favorable outcomes. What we want is the first player receive exactly 2 hearts. First player receive 5 cards. Then exactly 2 of the cards are hearts. The rest cannot be heart. First player receive exactly 2 hearts, and the rest cannot be hearts. We know that there are totally 13 hearts. Other than heart, there are 39 other cards. There are totally 13 hearts and 39 other cards. So, first player, he needs to choose 2 hearts out of 13. He first of all chooses 2 hearts out of 13. Then the other 3 cards cannot be hearts. He chooses 3 cards out of 39 other cards. That's how the first player makes choice. Then for player 2 and player 3, we don't care what they get. They may or may not receive hearts. So we put the rest of the cards together. Since the first player picked 5 cards already, if we put the rest of the cards together, there are 47 cards left. Then the second player chooses 5 cards out of 47. The third player chooses 5 cards from 42. When the second player makes a choice, there are 42 cards left. And then the third player chooses 5 cards out of 42. For the second and the third player, we don't care. They may or may not receive hearts. Then we can cancel the top and the bottom. What's left is 13 choose 2 times 39 choose 3. Over denominator is 52 choose 5. That's probability of A. And we know that probability of A, B, C, they are exactly the same. The chance that first player receives exactly 2 hearts, second player receives exactly 2 hearts, or the third player receives exactly 2 hearts, they are exactly the same. So we know that probability of A equal to probability of B equal to probability of C. They are all the same. Next, let's try to find probability of A intersection B. Probability of A intersection B says first player receives exactly 2 hearts, and the second player receives exactly 2 hearts. So probability is always number of favorable outcomes divided by the number of all possible outcomes. For the number of all possible outcomes, there are 3 players. Each player receives 5 cards. So the number of all possible outcomes is 52 choose 5, 47 choose 5. And 42 choose 5. That's the denominator, the number of all possible outcomes. For the numerator, number of favorable outcomes. First player and the second player, they both receive exactly 2 hearts. That's the first player, that's the second player. Second player also receives 2 hearts. Then the other 3 cards cannot be hearts. Second player also receives exactly 2 hearts. And the rest of 3 cards, these 3 cards cannot be hearts. Now let's make choice for the first player. First player, first of all, choose 2 hearts out of 13. Then the other 3 cards cannot be hearts, so choose 3 cards out of 39. That's 39, choose 3. Next, the second player. Second player also need 2 hearts. There are totally 13 hearts. Since first player already get 2 hearts, there are 11 hearts left. Since first player already picked 2 hearts, there are 11 hearts left for the second player. So second player choose 2 hearts out of 11. Then the other 3 cards cannot be hearts. And for the other cards here, first player already picked 3 hearts. First player already picked 3 cards. What's left is 36 cards. Second player will choose 3 cards out of 36. There are totally 39 other cards. First player already picked 3, so there are 36 left. Second player choose 3 out of 36. Then for the third player, we don't care if he receives hearts or not, so we mix the remaining cards together. We mixed the remaining cards together. There are totally 52 cards on the deck. First player pick 5 cards. Second player pick another 5 cards. So there are 42 cards left. There are 42 cards left for the third player. Third player choose 5 cards out of the remaining cards. He may or may not receive hearts. We don't care. Then if I simplify, I can cancel 42 choose 5 from top and the bottom. What's left is 13 choose 2. 39 choose 3 times 11 choose 2 times 36 choose 3 times 42 choose 5. Denominator is, cancel 42 choose 5 here. Denominator is 52 choose 5 times 47 choose 5. That's the denominator. Then we know that probability of A intersection B is the same as probability of A intersection C, and the same as probability of B intersection C. They're all the same. So we know that probability of A intersection B is the same as probability of A intersection C. The same as probability of B intersection C. They're all the same. Then next, let's try to find out what's probability of A intersection B intersection C. Next, we try to find what's probability of A intersection B intersection C. Probability of A intersection B intersection C means there's a probability that all 3 players, each player receive exactly 2 hearts. All 3 players, each player receive exactly 2 hearts. Probability is always number of favorable outcome divided by the number of all possible outcome. The number of all possible outcomes is 52 choose 5, 47 choose 5, 42 choose 5. There are 3 players. Each player receives 5 cards out of total of 52 cards. That's the denominator, number of all possible outcome. For the numerator, the number of favorable outcome, we want 3 players. Each player receives 2 hearts. So first player receives 2 hearts. Second player receives 2 hearts. Third player also receives 2 hearts. And the other 3 cards, they cannot be hearts. So that's we are looking for a probability that each player receives 2 hearts. Each player receives exactly 2 hearts. Now let's take care of the first player first. First player receives 2 hearts out of 13. He first of all get 2 hearts out of 13. Then the other 3 cards here cannot be hearts. He receives 3 hearts out of 39. That's 39 choose 3. That's the first player. Now second player choose 2 hearts from remaining cards. Second player choose 2 hearts out of 11, since first player already picked 2 hearts. Second player receives 2 hearts out of 11. Then for the other 3 cards, it cannot be hearts here. For the other 3 cards here, they cannot be hearts. For 39 other cards, first player already picked 3. So for the second player, there are 36 cards left. Second player choose 3 cards out of 36. Then for the third player, third player also need 2 hearts. He chose 2 hearts out of the remaining hearts. So there are 13 hearts. First player pick 2 hearts. Second player pick 2 hearts. So there are 9 hearts left. Third player will choose 2 hearts out of 9. Then for the remaining cards, there are 13 for the remaining 3 cards. A total is 39 other cards. First player picks 3. Second player picks 3. There are 33 cards left here. Third player will pick another 3 out of 33. Then that's probability of A intersection B intersection C. Then plug into this formula. Probability of A union B union C. If we plug in, we have probability of A plus probability of B plus probability of C. They are all the same. They are all the same. So we have 3 times 13 choose 2. 39 choose 2. 39 choose 3. Over 52 choose 5. Then minus probability of A intersection B, A intersection C, and B intersection C. They are all the same. So minus 3 times this number. 13 choose 2. 39 choose 3 times 11 choose 2. 36 choose 3. Over the denominator 52 choose 5. 47 choose 5. Then plus probability of A intersection B intersection C. Plus probability of A intersection B intersection C plus this number. That's 13 choose 2. 39 choose 3. 11 choose 2. 36 choose 3. 9 choose 2. 33 choose 3. Over the denominator 52 choose 5. 47 choose 5. 42 choose 5. Then I use my calculator. Then type everything to my calculator. I get 0.6446. Type everything to the calculator. I get 0.46. I get 0.6446. Part D. What's the probability that at least 2 players receive exactly 2 hearts? Let's set out the problem first. Let event A represent the first player. The first player receives exactly 2 hearts. Let event B represent the second player receives exactly 2 hearts. Let event C represent the third player receive exactly 2 hearts. We are looking for a probability that at least 2 players receive exactly 2 hearts. Let's draw a Venn diagram first. At least 2 players receive exactly 2 hearts. At least 2 players receive exactly 2 hearts means either the first 2 players receive 2 hearts, or the first and the third player receive 2 hearts, or the second and the third player receive 2 hearts. That's what we are looking for in the Venn diagram. That's what we are looking for. So for the shaded region, we can use probability of A intersection B plus probability of A intersection C plus probability of B intersection C. We can use probability of A intersection B plus probability of A intersection C plus probability of B intersection C. But here we overcome the middle region. Here we count it 3 times. A intersection B, A intersection C, B intersection C. We count it 3 times. But we're supposed to count it only once. We're supposed to count the middle region only once. Since we counted 3 times, to keep in balance, here we have to subtract the middle part twice. Subtract 2 times probability of A intersection B, intersection C. To keep in balance, I subtract the middle part twice. So A intersection B plus A intersection C plus B intersection C minus the middle part twice. That's the probability that at least 2 players receive exactly 2 hearts. And then if we observe part C and part D, we can see that the event ABC in part C and part D, they are exactly the same. The event ABC in part C and part D, they are exactly the same. At least first player received 2 hearts, second player received 2 hearts, third player received 2 hearts. First player received 2 hearts, second player received 2 hearts, third player received 2 hearts. So since event ABC in part C and part D, they are exactly the same. For probability A intersection B, A intersection C, B intersection C, and A intersection BC, A intersection B and C, I can use the same value from part C. In part C, we know that probability of A intersection B, A intersection C, and B intersection C, they are exactly the same. They all equal to this value. So we can write it here. Probability of A intersection B plus A intersection C plus B intersection C is equal to 3 times 13 choose 2 times 39 choose 3 times 11 choose 2 times 36 choose 3 over 52 choose 5 times 47 choose 5 minus twice probability of A intersection B intersection C. This is also the same as part C, equal to this. So let me put it here. 13 choose 2, 39 choose 3, 11 choose 2, 36 choose 3, 9 choose 2 times 33 choose 3, over denominator 52 choose 5. 47 choose 5. 42 choose 5. Then use calculator. Here I use my calculator. I get 0.1458. So that's the probability that at least 2 players receive exactly 2 hearts. Number 7, part A. A hand of 6 cards is drawn from a standard 52 card deck. Part A. What's the probability of getting 3 different pairs? We know that probability is always the number of feasible outcomes divided by the number of all possible outcomes. Let's find the denominator first, number of all possible outcomes. In how many ways can we draw 6 cards out of 52 cards? We know that when we draw cards, the order doesn't matter. We don't care which card we get first, but we care what we have. What card do we have? We don't care which card we get first, so the order doesn't matter. Since order doesn't matter, we use combination. So the number of ways of getting 6 cards out of 52 is 52 choose 6. That's the number of ways of getting 6 cards out of 52. That's the denominator. Number of all possible outcomes. Now for the number of feasible outcomes, we want to get 3 different pairs. 3 different pairs. Let me show you the cards here. That's a standard deck of 52 cards. 3 different pairs. One example, it could be 2, 2, 2. Jack, Jack, and Queen, Queen. That's called 3 different pairs. For 3 different pairs, we must choose 3 kinds of cards out of 13. We need to choose, first of all, choose 3 kinds of cards out of 13 first. So we first of all choose 3 kinds of cards out of 13. We first of all choose 3 kinds of cards out of 13 different kinds. Then for each kind, for example, if we choose 2, for each kind, there are 4 different suits. We have 2 of club, 2 of spade, 2 of heart, and 2 of diamond. For each kind of cards, there are 4 different suits. So if we pick 2, there are 4 different 2s. Now we need to choose 2 2s out of 4. That's 4 choose 2. Then same thing for jack. There are 4 different jacks. We choose 2 out of 4. That's 4 choose 2. Then for queens, there are 4 different queens. We choose 2 out of 4. That's 4 choose 2. That's the number of favorable outcome. Then take number of favorable outcome divided by the number of all possible outcome. That's the probability of getting 3 different pairs. And here I use my calculator. I get 0.003034. That's part A. For part B, what's the probability of getting 2 pairs? If we are getting 2 pairs, then we have 2 pairs here. The last 2 cards must have different rank. The last 2 cards, they must have different rank. For example, they must have different rank. So 2 pairs, and the other 2 cards must have different rank. Probability is always number of favorable outcome divided by the number of all possible outcome. The number of all possible outcome here is 52 choose 6. We are choosing 6 cards out of 52. For the number of favorable outcome, we take care of these 2 pairs first. For these 2 pairs, we must choose 2 rank out of 13. We choose 2 rank out of totally 13 rank. Choose 2 rank out of 13. Then for these 2 rank here, there are 4 different cards. We choose 2 cards out of 4. There are 4 2s. We choose 2 out of 4. There are 4 jack. We are choosing 2 out of 4. That's these 2 pairs. Next, we need to take care of these 2 single cards. For these 2 single cards, they must be 2 different ranks. They cannot be the same rank as these 2 pairs, and they must be 2 different rank here. Since we use 2 rank already, since we use 2 rank for these 2 pairs, there are 11 different rank left, and we choose 2 different rank for these 2 single cards. Then for each single card, for example, if I choose 9, there are 4 different 9s. I choose 1 out of 4. And if I choose king, there are 4 different kings. I choose 1 out of 4. That's a numerator, the number of favorable outcome. 13 choose 2. 4 choose 2. 4 choose 2 times 11 choose 2 times 4 choose 1, 4 choose 1. Then use calculator. This calculator here, I get 0.1214. That's the probability of getting 2 pairs. Part C. What's the probability of getting 3 of a kind? What's the probability of getting 3 of a kind? That means 3 cards have the same rank. For example, I get 5, 5, 5. 3 cards of the same rank. The other 3 cards have different rank. Say 7, jack, and king. We have 3 cards with the same rank. The other 3 cards have different ranks. So let's take care of this triple of cards first. For this triple of cards, I first of all choose a rank. 13 choose 1. I first of all choose a rank out of 13. I first of all choose 1 rank out of 13. For example, if I pick 5, there are 4 different 5s. If I pick number 5, there are 4 different 5s. 5 of club, 5 of spade, 5 of heart, 5 of diamond. There are 4 different 5s. I choose 3 5 out of 4. Then let's take care of these 3 single cards. For these single cards, they all have different ranks, and their rank must be different as this triple of cards. So once I pick the triple of cards, there are 12 other rank left. I choose 3 different rank out of 12. Then for each single cards, for example, if I pick 7, there are 4 different 7s. I choose 1 out of 4. If I pick jack, there are 4 different jacks. I choose 1 out of 4. If I pick king, there are 4 different kings, so I choose 1 out of 4. That's the numerator, the number of favorable outcome. Number of favorable outcome. 13 choose 1, 4 choose 3 times, 12 choose 3, 4 choose 1 times 4 choose 1 times 4 choose 1, over the number of all possible outcome. For the number of all possible outcome, we are choosing 6 cards out of 52. That's 52 choose 6. Then use calculator. I have 0.03596. That's part C. Part D. What's the probability of getting all cards within the same suit? What's the probability of getting all cards within the same suit? So for probability, keep in mind, it's always number of favorable outcome divided by number of all possible outcome. Number of all possible outcome is 52 choose 6. For the number of favorable outcome, we want all cards within the same suit. In how many ways can we choose all cards within the same suit? We know there are 4 different suits: club, spade, heart, and diamond. We first of all choose 1 suit out of 4. First of all, choose 1 suit out of 4. Then, for each suit, there are 13 different cards. We choose 6 cards. We choose 6 cards out of 13. So first of all, choose 1 suit out of 4. For example, if I choose spade, there are 13 spades. I choose 6 out of 13. That's part D. Then use calculator. I get 0.1. I get 0.0003372. Number A. A bag contains 7 red marbles, 8 green marbles, and 10 marbles. 5 marbles are randomly drawn from the bag. Part A. If it's known that the first 2 of the marbles are blue, what's the probability that the other 3 marbles are red? So for number A, some condition is given. This is called conditional probability. Let's set down the problem first. Let event A be the event that the first 2 marbles are blue. Let B be the event that the other 3 marbles are red. That means the last 3 marbles are red. The last 3 marbles are red. So we are looking for probability of B given A. Given the first 2 marbles are blue, what's the probability that the other 3 marbles are red? Use the formula. Use the formula for conditional probability. This can be rewritten as probability of A intersection B over probability of A. The denominator must be the condition. The denominator must be the condition here. So let's find each probability individually, then divide. Let's find each probability individually, then divide. Let's find denominator first. Let's find probability of A first. Remember, for probability, it's always number of favorable outcome divided by the number of all possible outcome. What's the number of all possible outcome? There are 7 red marbles, 8 green marbles, and 10 blue marbles. Totally 25 marbles. There are totally 25 marbles. We are choosing 5 marbles randomly. We are choosing 5 marbles randomly out of 25. Now, does an order matter? Does an order matter? If an order matters, we use permutation. If an order doesn't matter, we use combination. Does an order matters? Here, since the problem specifies the first 2 marbles, first 2 marbles, that means the order matters. They cares what we get first. We care what we get first. Since the problem specifies the first 2 marbles, that means they care about the order. They care about what we get first. Since the problem specifies an order, it means order matters. So use permutation. Since the problem specifies orders, since the problem specifies the first marble, second marble, the order matters. We use permutation. So for the denominator, we are choosing 5 marble out of 25. That's permutation. 25, choose 5. That's the denominator. Number of all possible outcomes. Now, numerator. Number of favorable outcomes. First 2 marbles are blue. What's the probability that the first 2 marbles are blue? We are getting 5 marbles. Order matters. First 2 marbles are blue. That means we are choosing 2 blue marbles out of 10. That means for the first 2 marbles, we are choosing 2 blue marbles out of 10. So for the first two blue marbles, we are choosing 2 marbles out of 10. And for the last 3 marbles, we don't care. We only care about the first 2 marbles is blue. We don't care about the last 3 marbles. There are totally 25 marbles. If I choose 2 blue marbles, put it here. There are 23 marbles left. If I choose 2 blue marbles here, we have 23 marbles left. For the other 3 marbles, it may or may not be blue. We don't care. It may or may not be blue. So we're choosing 3 marbles from the remaining marbles, which is permutation 23, choose 3. So here, I first of all choose 2 blue marbles out of 10. Then there are 23 marbles left. Then I choose 3 more marbles out of 23. These marbles, it may or may not be blue. We don't care. Let me note it here. So for probability of A, number of all possible outcomes, 25, choose 5. We are choosing 5 marbles out of 25. For the numerator, we want the first 2 marbles to be blue. So we are choosing 2 blue marbles out of 10. That's permutation, 10, choose 2. Then, since I picked 2 blue marbles, there are out of 25, there are 23 marbles left. For the last 3 marbles, we don't care what color it is. It may or may not be blue. So we're choosing the other 3 marbles out of 23. That's the denominator, probability of A. Now for the numerator, probability of A intersection B. The denominator is always the number of all possible outcomes. That's permutation 25, choose 5. For the numerator, that's the number of favorable outcomes. A intersection B represents that the first 2 marbles are blue and the last 3 marbles are red. So A intersection B says the first 2 marbles are blue and the last 3 marbles are red. So for the first 2 marbles, we are choosing 2 blue marbles out of 10. For the last 3 marbles, since they must be red, we are choosing 3 red marbles out of 7. We choose 3 red marbles out of 7. Since order matters, that's permutation 7, choose 3. Then, for probability of B given A, use the formula. Probability of A intersection B divided by probability of A. Probability of A is permutation 10, choose 2 times permutation 23, choose 3 divided by permutation 25, choose 5. Then here we can use calculator. I use calculator, I get 5 over 253. That's part A. Part B, if it's known that the first marble is green, what's the probability that the last marble is also green? So this is also conditional probability. When some conditional is given here, this is conditional probability. Let's set down the problem first. Let A be the event that the first marble is green. let B be the event that the last marble is green. We are looking for the probability given the first marble is green. If the first marble is green, what's the probability that the last marble is also green? So that's conditional probability. The formula can be written as probability of A intersection B over probability of A. That's how we set out the problem. Then we find probability for each of them, then divide the answer. Let's find probability of A first. For probability of A, remember, for probability is always number of favorable outcome divided by the number of all possible outcome. Let's find the number of all possible outcome first. Let's find the number of all possible outcome first. Here, does the order matters? Does the order matter? In this problem, in part B, since we specify the first marble and the last marble, that means the order matters. Since we specify the first marble and the last marble, that means order matters. If order matter, we use permutation. So we are choosing 5 marble out of 25. There are totally 7 red marble, 8 green marble, 10 blue marbles. There are totally 25 marbles. And we are choosing 5 marbles out of 25. So denominator is permutation, 25 choose 5. We are choosing 5 marbles out of 25. That's the denominator, number of all possible outcome. The numerator, for the numerator, the number of favorable outcome. What we want is probability of A. Probability of A represents that the first marble is green. First marble is green. We only care about the first one. We only care about the first one. So for the first marble, we are choosing 1 green marble out of A. That's number of choice for the first green marble. We're choosing 1 green marble out of A. Order matters. That's permutation. Then for the other 4 marbles here, we don't care. They may or may not be green. So since I only pick 1 marble out of 25, there are 24 marbles left. Since I pick 1 marble for the first marble here, there are 24 marbles left. And for the other 4 marbles, we don't care about the color. They may or may not be green. We don't care about the color. So we choose 4 more marble out of the rest. That's permutation. 24 choose 4. This is the denominator. Now for the numerator, probability of A intersection B. Again, probability is always number of favorable outcome divided by the number of all possible outcome. So denominator is permutation 25 choose 5. We are choosing 5 marble out of 25, and order matters. So we use permutation 25 choose 5. That's the denominator, the number of all possible outcome. Now for the numerator, the number of favorable outcome, it must satisfy both A and B. The first marble is green, and the last marble is green. The first marble is green, and the last marble is green. So let's make choice for these 2 places first. Let's make choice for these 2 places first. Since the order matters, we use permutation. We are choosing 2 green marbles out of A. Choose 2 green marbles, put in the first place and the last place. Since the order matters, we use permutation. So permutation A choose 2. Choose 2 green marbles. Then for the other 3 marbles here, we don't care about the color. They may or may not be green. We don't care about the color. Since we pick 2 marbles already, there are 23 marbles left. Since we picked 2 marbles already, there are 23 marbles left. We pick 3 more marbles, put it here in the middle. That's permutation 23 choose 3. Then we can see that this is the numerator, this is the denominator. Then divide. So probability of B given A. This is the numerator. Permutation A choose 2 times permutation 23 choose 3 divided by permutation 25 choose 5. Then for the denominator is probability of A. This is probability of A. permutation A choose 1 times permutation 24 choose 4 divided by permutation 25 choose 5. So plugging these two probabilities into this formula. This is the numerator, this is the denominator. Then divide. Use your calculator. Here I use my calculator. I get 7 over 24. Here I use my calculator, I get 7 over 24. Part C. If it's known that none of the marbles are red, what's the probability that there are more green marbles than blue marbles? So this is again conditional probability. Let's set out the problem first. Let A be the event that none of the marbles are red. Let B be the event that there are more green marbles than blue marbles. There are more green marbles than blue marbles. This is conditional probability. The condition is that none of the marbles are red. We're looking for the probability that there are more green marbles than blue marble. That's event B. Then use the formula. Use the formula. This conditional probability can be rewritten as probability A intersection B over probability of A. The denominator is always a condition. Then we find each probability individually. Then divide the answer. Let's find denominator first. Probability of A. Remember, probability is always the number of favorable outcome divided by the number of all possible outcome. For the number of all possible outcome, we are choosing 5 marbles out of 25. There are 7 red marbles, 8 green marbles, 10 blue marbles. That means there are totally 25 marbles. We are choosing 5 marbles out of 25. Now in part C, does an order matter? If none of the marbles are red, what's the probability that there are more green marbles than blue marbles? Do we care about which marble we get first? Since in part C, the problem doesn't specify an order, that means the order doesn't matter. We don't care which marble we get first. We care what marble we have. So in part C, order doesn't matter. If an order doesn't matter, we use combination. So for denominator, the number of all possible outcomes, we are choosing 5 marbles out of 25. Since the order doesn't matter, we use combination. 25 choose 5. That's the denominator. Now for numerator, number of favorable outcome. None of the marbles are red. If we don't pick red marble, that means we only pick green or blue marbles. If we don't pick red marble, means only pick red or green marbles. And we need to choose a total of 5 marbles. So we are choosing 5 marbles out of 18. Since we can't pick red marble, that means we can only pick green or blue marble, which is that's a total of 18. So we are choosing 5 marble out of total of 18. That's probability of A. Next, let's try to find probability of A intersection B. Probability is always number of favorable outcome divided by the number of all possible outcome. For the number of all possible outcome, we are choosing 5 marbles out of 25. That's permutation 25 choose 5. So that's combination 25 choose 5. Since order doesn't matter, we use combination. Combination 25 choose 5. That's denominator, the set of all possible outcomes. Now for the numerator, we try to find the number of favorable outcome. For the numerator, we try to find the number of favorable outcome. What we want is none of the marbles are red, and there are more green marbles than blue marble. None of the marbles are red, and there are more green marbles than blue marbles. So, if none of the marbles are red, there are more green marble than blue marble. We may have 3 green marble, 2 blue marble, or 4 green marble, or 4 green marbles. Four green marbles, 1 blue marble, or 5 green marbles, 0 blue marbles. So if there are no red marble and more green marble than blue marble, that means we may have 3 green marble, 2 blue marble, 4 green marble, 1 blue marble, or all 5 green marbles. So there are 3 cases. First case, 3 green marble, 2 blue marble. We are choosing 3 green marble out of A, and two blue marbles out of 10. It's combination, this order doesn't matter. Second case, 4 green marbles out of A, or 1 blue marbles out of 10. In last case, 5 green marbles. That's the numerator, probability of A intersection B. Then for the conditional probability, B given A, we use the numerator divided by the denominator. This is the numerator. This is the numerator. The denominator is probability of A, which is 18 choose 5 over 25 choose 5. Then use calculator. Here, use calculator, I get 13 choose 34. Part D, if it's known that there are the same number of red and green marbles, what's the probability that only one of the marbles is blue? So this is a conditional probability problem. Let's set out the problem first. Let event A represent there are the same number of red and green marbles. There are the same number of red and green marbles. Let event A represent that there are the same number of red and green marbles. Let event B represent that only one of the marbles is blue. Only one of the marbles is blue. So in this problem, we are looking for probability of B given A. The condition is that there are the same number of red and green marbles. That's a condition. What we are looking for is only one of the marbles is blue, which is B, which is event B. Then use the formula for conditional probability. Use the formula for conditional probability. This can be rewritten as probability of A intersection B over probability of A. Then we find each probability individually. Let's find the denominator first. Probability of A. There are the same number of red and green marbles. Remember, probability is always number of favorable outcome divided by the number of all possible outcome. In this problem, the denominator is we are choosing 5 marbles out of 25. We have 7 red marble, 8 green marble, 10 blue marbles. Totally there are 25. We are choosing 5 marbles out of 25. Now in part D, does an order matters? Does an order matter? If an order matters, we use permutation. If an order doesn't matter, we use combination. Does the order matter here? If it's known that there are the same number of red and green marble, what's the probability only one of the marble is blue? So we don't care about which marble we get first. We care about what marble we have. We don't care about what marble we get first. So the order doesn't matter. Since the order doesn't matter, we use combination. So for the denominator, we are choosing 5 marbles out of 25. For the denominator, the number of ways of choosing 5 marbles out of 25 is 25 choose 5. That's the number of ways of choosing 5 marbles out of 25. That's the number of all possible outcomes. Now for the numerator, the number of favorable outcome, we are looking for the same number of red and green marbles. The same number of red and green marbles. We may have 0 red, 0 green, 5 blue. That's one possibility. Or we may have 1 red, 1 green, 3 blue. That's another possibility. Same number of red and green marbles. Or we may have 2 red, 2 green, and 1 blue marble. That's another possibility. The same number of red and green marbles. So those are the only possibilities for the same numbers of red and blue marbles. So case 1, 0 green, 0 red, 0 green, 5 blue marble. That means we are choosing 5 blue marble out of 10. So the number of ways of getting 5 blue marble out of 10 is 10 choose 5. That's the number of ways of getting 5 blue marble out of 10. Case 2, 1 red marble, 1 green marble, and 3 blue marble. There are 7 red marbles. We are choosing 1 red marble out of 7. There are 8 green marbles. We are choosing 1 green marble out of 8. And there are 10 blue marbles. We are choosing 3 blue marble out of 10. That's case 2. That's the number of ways of getting 1 red marble, 1 green marble, and 3 blue marbles. Case 2. Case 3. In how many ways can we get 2 red marble, 2 green marble, and 1 blue marbles? We can choose 2 red marble out of 7, 2 green marble out of 8, and 1 blue marble out of 10. That's the number of ways of getting 2 red marble, 2 green marble, and 1 blue marble out of 25. That's probability of A. Next, for probability of A intersection B, do the same thing. Probability is number of favorable outcome divided by the number of all possible outcome. For the number of all possible outcome, we are choosing 5 marbles out of 25, and order matters. And the order doesn't matter, it's combination. We are choosing 5 marbles out of 25. Order doesn't matter, we use combination. Then for the numerator, we must consider both even A and even B. There are the same number of red and green marbles, and only one of the marbles is blue. There are the same number of red and green marbles, and only one of the marbles is blue. That's the only possibility. Same number of red and green marbles, and only one of the marbles is blue. That's the only possibility. So, in how many ways can we choose 2 red marble, 2 green marble, and 1 blue marble? So the number of ways to choose 2 red marble out of 7 is 7 choose 2. The number of ways to choose 2 green marbles out of 8 is 8 choose 2. The number of ways to choose 1 blue marble out of 10 is 10 choose 1. Then multiply together. That's probability of A intersection B. Then for the conditional probability, probability of B given A, this is a numerator, probability of A intersection B, and this is a denominator, probability of A. So let's put them together and divide. We have 7 choose 2, A choose 2, 10 choose 1, over 25 choose 5. The denominator is probability of A, which is this. 10 choose 5 plus 7 choose 1, A choose 1, 10 choose 3 plus 7 choose 2, A choose 2, 10 choose 1, over 25 choose 5. Then use calculator for the rest. Here I use my calculator. I get 70 over 153. Number 9. John is currently taking a calculus class, and he will have a test next week. He estimates that if he studies over the weekend, he will have a 70% chance to pass the test. And if he doesn't study over the weekend, he only has 20% chance to pass the test. Assume John's estimation is correct, and John has a 90% chance to study over the weekend. Part A. What's the probability that John will pass the test? So for number 9, let's first of all translate the problem first. Let's first of all set a problem and translate first. Let event A represent that John study over the weekend. Let event A represent that John study over the weekend. Let event B represent John passed the test. Let event A represent John study over the weekend. Let event B represent John passed the test. Let's write down all given probabilities here. He estimates that if he study over the weekend, he has 70% chance to pass. So if John study over the weekend, the chance he passed the test is 70%. That's first given probability here. If he study over the weekend, the chance he passed the test is 70%. And if he doesn't study over the weekend, the chance he pass is 20%. If he doesn't study over the weekend, the chance he passes the test is 20%. What else is given? John has a 90% chance to study over the weekend. Probability of A is 90%. John has a 90% chance to study over the weekend. So probability that he study is 90%. In part A, what we are looking for is what's the probability that John will pass the test? Part A, what's the probability that John will pass the test? So what we are looking for in part A is probability of B. What's the probability that John will pass the test? So here, in order to find probability of B, we can try to use the law of total probability. In order to find probability of B, we can try to use the law of total probability. Use the law of total probability. If John passed the test, there are two cases, there are two conditions. Either he studied over the weekend, he passed the test. Or he doesn't study over the weekend, but he still have some chance to pass the test. So if John passed the test, there are two cases. Either he studied over the weekend, then he passed. or he doesn't study over the weekend, but he still have some very, very little chance to pass the test, then use multiplication rule to rewrite this. Probability of A intersection B can be rewritten as probability of A times probability of B given A. Then for the second part, I can write it as probability of A complement times probability of B given A complement. Then plug in the numbers. Probability of A is 0.90. Probability of B given A is 0.70. Probability of A complement, since probability of A is 90, probability of A complement, I can use 1 minus probability of A, which is 0.10. Probability of B given A complement, that's 0.20. Then that's 0.63 plus 0.02, which is 0.65. That's the chance that John will pass the test. That's the chance that John will pass the test. Part B. If it's known that John passed the test, what's the probability that he doesn't study over the weekend? Part B. If it's known that John passed the test, what's the probability that he doesn't study over the weekend? So what's given is that John passed the test. That's B. What's given is that John passed the test. What's the probability that he doesn't study over the weekend? What's the probability that he doesn't study over the weekend? That's A complement. So if it's known that John passed the test, what's the probability that he doesn't study over the weekend? A complement represents John doesn't study over the weekend. Then use the formula for conditional probability. This can be rewritten as probability of A complement intersection B over probability of B, where B is a condition. B is a condition. Then probability of A complement intersection B, we can use multiplication rule. For the numerator, probability of A intersection B, I can use multiplication rule. That can be rewritten as probability of A complement times probability of B given A complement. Use multiplication rule. This can be rewritten as probability of A complement times probability of B given A complement over probability of B. Then plug in numbers. Plug in the numbers. Probability of A complement is 0.10. Probability of B given A complement is 0.20. Probability of B. From part A, we know that probability of B is 0.65. So numerator is 0.02. Denominator is 0.65. Together is 2 over 65. So if John passes the test, the chance he doesn't study is 2 over 65. Part C. If it's known that John failed the test, what's the probability he study over the weekend? If it's known that John failed the test, what's the probability that he did study over the weekend? So what's given is that John failed the test. That's a condition. That's B complement. What's given is that John failed the test, which means he doesn't pass. That's B complement. What we're looking for is the probability that he studied over the weekend. What's the probability that John studied over the weekend if he failed the test? So he failed the test, it's a condition. If it's known that John failed the test, what's the probability that he studied over the weekend? Then use the formula. This can be rewritten as probability of A intersection B complement over probability of B complement. probability of A intersection B complement that can be rewrite as on the numerator. A intersection B complement, assume let's set A, let's set B. A intersection B complement is this part. That's probability of A. That's probability of A minus probability of A intersection B. That's probability of A minus probability of A intersection B. And probability of B complement can be rewrite as 1 minus probability of B. Then the numerator, we know probability of A. Probability of A intersection B, we can use multiplication rule. Probability of A intersection B, we can use multiplication rule. That can be rewrite as probability of A times probability of B given A. Over 1 minus probability of B. Then plugging the numbers. Probability of A is 0.90. Probability of A is 0.90. Probability of B given A is 0.70. Probability of B given A is 0.70. Over 1 minus probability of B. Probability of B from part A, we know that that's 0.65. Then on the numerator, I have 0.90 minus 0.63. On the denominator, I get 0.35, which is 0.27 over 0.35. That's 27 over 35. Number 10. Box A has 3 green marbles, 1 red marbles. Box A has 3 green marble, 1 red marble. Box B has 4 green marbles and 2 red marbles. And box C has 5 green marbles and 3 red marbles. There are 3 boxes. Box A has 3 green marbles, 1 red marble. Box B has 4 green marbles, 2 red marble. Box C has 5 green marble, 3 red marble. Peter roll a die first. If the die comes up 1, he randomly chooses a marble from box A. If the die comes up 2 or 3, he randomly chooses a marble from box B. If the die comes up 4, 5, or 6, he randomly chooses a marble from box C. Part A. What's the probability that Peter get a red marble? So let's set down the problem first. Let event A represent that Peter choose a marble from box A. Let event A represent that Peter choose a marble from box A. Let event B represent that Peter choose a marble from box B. Let event C represent that Peter choose a marble from box C. And there are two types of marbles, green marble and red marble. Let G represent Peter choose a green marble. Let G represent that Peter choose a green marble. Let R represent Peter choose a red marble. Now, what's known? What's given here? What do we know here? Probability of A. If the die count up 1, Peter will choose a marble from box A. That means the chance that Peter chooses a marble from box A is 1 out of 6. If the die count up 1, Peter chooses a marble from box A. That means the chance that the probability that Peter pick marble from box A is 1 over 6. Probability of B. If the die count up 2 or 3, Peter will choose a marble from box B. So the chance that Peter will choose a marble from box B is 2 over 6. If the dice count up 2 or 3, that's 2 outcomes out of 6. That's 2 outcomes out of 6. When we roll a die, there are 6 outcomes. 2 or 3 is 2 outcomes out of 6. So the probability that Peter will choose a marble from box B is 2 over 6. Probability of C. What's the chance that Peter will pick marble from box C? We know that if the die count up 4, 5, or 6, Peter will choose a marble from box C. So the probability that Peter will choose a marble from box C is 3 out of 6. 4, 5, 6, there are 3 outcomes out of 6 outcomes. 4, 5, 6, when we roll a die, there are 6 outcomes. 4, 5, 6, there are 3 outcomes out of 6. So that's probability of A, B, and C. Now let's answer the question here. Part A. What's the probability that Peter gets a red marble? What's the probability that Peter gets a red marble? So we're looking for probability that Peter gets a red marble. That's what we are looking for in part A. What's the probability that Peter gets a red marble? Then use the law of total probability. If Peter gets a red marble, then he may get a red marble from box A. He may go to box A and get a red marble, or he may go to box B and get a red marble. Or he may go to box C and get a red marble. That's the law of total probability. If Peter gets a red marble, he may go to box A and get a red marble, or go to box B, get a red marble, or go to box C and get a red marble. Then use multiplication rule. Probability of A intersection R can be rewritten as probability of A times probability of red given A plus probability of B times probability of red given B plus probability of C times red given C. Probability of A. The probability that he will choose a marble from box A is 1 over 6. Probability of red given A is asking the probability in box A. If he pick marble in box A, if he pick marble in box A, what's the chance that he get a red marble? If he pick marble in box A, what's the chance that he get a red marble? In box A, the chance of getting red marble is 1 out of 4. Plus probability of B. Probability of B is 2 over 6. Times probability of R given B. This is a probability that if he go to box B, what's the chance that he will pick up a red marble? If we go to box B, what's the chance that he will get a red marble? In box B, the chance of getting red marble is 2 out of 6. In box B, the chance of getting red marble is 2 out of 6. Probability of C is 3 over 6. And this probability here, probability of red given C, this is asking if he go to box C, what's the chance that he will get a red marble? If he go to box C, what's the chance that he will get a red marble? In box C, the chance of getting red marble is 3 out of 8. Then multiply and add together. Here I use my calculator. I get 49 over 144. Multiply and add together. Part B. If it's known that Peter gets a red marble, what's the probability that the marble is chosen from box A? So in part B here, if it's known that Peter gets a red marble, so that's a condition. It's known that Peter gets a red marble. What's the probability that the marble is chosen from box A? If it's known that Peter gets a red marble, what's the probability that the marble is chosen from box A? Use the formula for conditional probability. That's A intersection R over probability of R. The denominator is always the probability of the condition. Denominator is always the probability of the condition. Then for the numerator, we can use multiplication rule. Probability of A intersection R can be rewritten as probability of A times probability of R given A. Leave the bottom the same. Then we can plug in the numbers. Probability of A. Probability of A is 1 over 6. Probability of R given A. That means in box A, what's the probability of getting a red marble? In box A, what's the probability of getting a red marble? In box A, the probability of getting a red marble is 1 out of 4. That's the numerator. The denominator, probability of R. In part A, we know that probability of R is 49 over 144. Then use calculator, I get 6 over 49. Part C. Part C. If it's known that Peter gets a green marble, what's the probability that the marble is chosen from box C? So this is conditional probability. If it's known that Peter gets a green marble, what's the probability that the marble is chosen from box C? That's the problem. Probability that Peter gets a green marble. What's the probability he gets the marble from box C? Then use the formula. Use the formula for conditional probability. This can be rewritten as probability of C intersection G over probability of G. Numerator, if I use multiplication rule, it can be rewritten as probability of C times probability of C given G. G given C, sorry. If I use multiplication rule, that can be rewritten as probability of C times probability of G given C. That's a numerator. The denominator, what's the probability of getting green marble? We know there are only two types of marbles, either red or green. If we don't get red marble, then we must get green marble. If Peter doesn't get red marble, he must get green marbles. So the chance of getting green marble is the same as the chance that he doesn't get a red marble. The chance that Peter gets a green marble is the same as that Peter doesn't get a red marble. There's only two colors of marbles, either red or green. If he gets a red marble, that means he doesn't get a red marble. If Peter gets a green marble, means he doesn't get a red marble. So that's probability of red complement, R complement. And we know that probability of R complement is 1 minus probability of R. The numerator is probability of C times probability of G given C. Probability of C is 3 over 6. Probability of green given C. Probability of green given C. That means what's the probability of getting green marble in box C? What's the probability of getting green marble in box C? In box C, the chance of getting green marble is 5 out of A. In box C, the chance of getting green marble is 5 out of A. And denominator, probability of getting red marble. From part A, we know that probability of getting red marble is 49 over 144. Then use calculator. Here I get 9 over 19.